People are entering the room, so let's just give them a second.
Sure. Let's wait.
Is going on.
Yeah, let's wait a few minutes. Would that work?
Probably just another 30 seconds or so.
Okay, that's fine.
You should be able to see in the participant list that people are entering the room. So just give them.
Here we go. Hello, everyone. I kindly ask if you can help the other speaker and provide him with an update link.
Yes, I'm on it.
Thank you. He's having trouble and I can't manage right now, please.
Yeah, no worries, I'm on it.
Thanks.
I think we can get the ball rolling here.
Yeah, I think we can start if that works for everyone. Okay, that works for me, so that's great. Fantastic. So hello, everyone. My name is Ilaria Sinelli, and I'm the guest editor. And today we are going to have a nice webinar about a special issue entitled Healthcare for Space, Space for Healthcare. So this is the agenda, and we are going to have an opening remarks by our editor-in-chief. Then we are going to have presentation. Those are quite short presentation, 5-7 minutes presentation by our speaker, a little bit of open discussion, and then we are going to have discussion with 2 guest speakers. And so I invite the editor-in-chief to tell us something about the journal, please.
Thank you very much. Dr. Sinelli really has done a fantastic job with this special issue that we launched about a year ago now, and we got really fantastic contributions. This is a relatively new journal by IEEE, sponsored by the Engineering Medicine Biology Society. Thanks to outstanding area editors like Dr. Sinelli and the rest of our OJMB, Open Journal of Engineering Medicine Biology team. We're doing really, really well. We got our first impact factor 5.8 recently. We got our partial size score, which, as you know, is estimated over 4 years, although the journal has been in place only for 3. And so we got our partial score 7.8. And I just checked on the size score tracker, we're at 9.4 at the moment. So we really have a fantastic team that it's moving the numbers of the journals up. I want to thank Dr. Sinelli for doing a fantastic job with this special issue, extremely interesting. So we're going to have really exciting talks, and I want to thank everybody for connecting. I can see in the webinar chat from all over the world. So looking forward at the presentations and then the discussions. Thank you so much, Ila.
You're welcome. And I will to tell you something a little bit more about the special issue. Today is a sort of celebration day. We are celebrating our speaker. We are celebrating their work. And this is something very close to my heart because, you know, I have a personal life mission and which is about space and healthcare. And I successfully trapped the editor in this very long mission, very long adventure. We announced the special issue summer last year. We closed it, and every manuscript that we are going to discuss today are in early access, so you're free to read it and to read them anytime. And it's, you know, you can publish with the OGMB even if the paper won't then appear in the special issues. So the journal still accepts space-related teams. So before starting, I want to thank the editor and the reviewer, because this is a very long journey, and I'm very, very happy that we made it all together, and I'm very happy that you are about to discover more and more about space and healthcare and how the two are very closely connected. And so I will leave the floor to Dr. Leine for presenting his work.
Well, thank you, Dr. Sinelli and Dr. Bernardo. All right, well, I'll try and run through this with you all and maintain the time that we need to. This was a paper that was presented for work that was done with the Human Research Program at NASA on Earth-independent medical operations. It's more or less a high-level overview of what is going to be necessary as you start considering deep space exploration. And these are the participants that helped helped build this work, and the images are credited as they are on the slides. Most of the slides here are taken from previous presentations, just so you're aware if they don't quite line up with dates. This is the fundamental problem. This is us, the picture is taken on the surface of Mars looking back at Earth. And that little dot in the sky is the nearest trauma center. So imagine having a medical emergency or even a minor problem, and your nearest 911 response is 165 million miles away. That is the challenge that we're dealing with fundamentally. And that is, when you're talking about this deep space exploration, it is a challenge of distance from Earth. And the fact that light has a limited speed means that communications are delayed. So it takes a longer time to receive feedback or guidance as a result of the distance from Earth. And that means that you have to then cram all of those people that are sitting in mission control. Think of the International Space Station today as having a crew of 6 on board and a crew of over 100 people on the ground supporting it. Right now, that works because of telecommunications like this. But if you're going to travel further away, that communication link disappears. A signal to Mars takes it could take as long as a 45-minute round trip. So imagine me having this conversation and then you not receiving that message for almost 20 minutes later, and then me not getting a response back afterwards. It's a very long Q&A. So with a medical emergency, that's not sustainable. We need to cram mission controls expertise into the space vehicle and send them off. That is challenging, to say the least. So how do we meet that? And this is what we've decided as the working definition for the field, which is that IMO, Earth Independent Medical Operations, is the transition of medical primacy from terrestrial to space-based assets to enable support of astronaut health and performance. This is a process enabling progressively resilient deep space exploration systems and crews to reduce risk and increase mission success. And we can go through the rest of this later on, but it's in the paper. It's basically a progressive work that's going to start here, move further out, and become progressively more independent as we go. So this is why. Now think of why we need to do this. We've never really had a major medical event in spaceflight, and this is sort of a description of that. This is work that was done on predictive software to tell what risk is going forward. And that this is showing that during the shuttle missions, this little red bar here is your medical risk. And on shorter missions, you have less medical risk. That makes sense. Most people can be able to predict that they'll stay healthy for 14 days. But when you start going out to these more than 700-day Mars missions, that red bar starts to get bigger. And this is what we're trying to tackle. The mission risk of loss of crew life in this case, makes up almost 1/3 of our estimated total mission risk. That means we got to do something about it. And that's what this is all about. Another thing we're thinking of is just looking at the pace of launches over the course of the last few years. The number of on-orbit person years has increased. That's going to mean we need a more robust system to manage multiple vehicles flying with multiple people as we start switching into the commercial sector. Other things to pay attention to, that it's not just about deep space. It's about needing to have independence on the orbital vehicles as we start to expand the population working up there. And what we did is basically break down this stuff into the major challenges that we're going to be facing. And this is what we came up with, that there are 5 major domains. So we need to be establishing robust pre-mission planning. What do you pack? Then figuring out what do you do when your preparation and prevention doesn't work. We're very good with preventive medicine now, but that prevention, even the best prevention, will fail over time. So we have to be ready for that contingency. Prolonged decision-making, meaning how do you facilitate decision-making when you have that delay in communication, and supplies and resource management. We can't resupply you if you are a year away from Earth. So how do we manage those supplies and triage that? And then task loading. How do we make sure that the crew doesn't get overwhelmed? And to do that, we're looking at real-world examples in test bed form now. So this is a risk assessment tool that we use, similarly to generating that earlier graphic, that talks about that helps us assess what we can pack to reduce that risk to the lowest possible amount. So this is a pre-mission planning tool that NASA is using. The current version of this is under development, called Impact, that's designed to assist us in building the requirements for the medical system so we don't leave anything behind, and we can estimate what the medical risk is to give us an informed consent about what that mission actually would be and the risk is. This is a model of what that program does. I won't get too much into the details, but if you're curious, it's probabilistic risk assessment. It's a well-established tool. And then we can also look at real-world examples. We have independent medical examples, some from the 1700s. This is a representation of Jim Cook's ships treating patients with scurvy. And that actually led to one of the first randomized controlled trials in medicine. This is a very good example of the early stages of science applied to healthcare in an exploration space, which is exactly what this journal is talking about. And then there's also the USS Sea Dragon, which is a fascinating story of basically improvised medical care when on a World War II submarine under the Pacific in a war zone. They had no external communication. They had to perform an appendectomy. They had no doctor. So they used just-in-time training, read a medical textbook and said, hey, I can do this surgery, and then performed it. Luckily, the person on board wasn't a doctor, but did have extensive surgical training. He was a surgical tech that essentially was independently performing appendectomies. The patient lived, by the way. It's a fascinating story if you're curious about it, but it gives us illustrations about what's necessary for success, because for every one of these success stories, there's a lot more that did not go that well. And this gives us clues as to how we can do it. So we can draw from previous experience, draw from predictive analytics and software tools, and build systems in place that would likely be enabling technologies like artificial intelligence, clinical decision support systems, not replacing physicians, but extending them. And with that, we can take these science fiction stories that we're all very familiar with, combine them with real world mission control, and stick them on these capsules in the real world traveling further from Earth. This is from the Artemis II test mission, where we actually flew a vehicle out further than we've ever done before. And this is the real world. We're no longer in the science fiction space in this regard. We're actually in that moment. So this is why Earth independent medical operations as an ongoing progressive work is a critically important piece of our process. So I will turn it back to you. Thank you all for paying attention. And I really appreciate, again, the editorial team here for giving me this.
Thank you so much, Dr. Levine. This is wonderful. And I will go on with the next speaker. I kindly remind you, everyone, to please stay on track. Otherwise, we're going to take too much time to our attendees. So, Professor Nowin, please, the floor is yours.
Okay, thank you very much for the opportunity today. It's a great panel of individuals to speak with. So here's the title of our paper. So this is work done by my amazing student, doctoral student, Songmi Song. I encourage everyone to take a look at the article through the journal. But the basic premise of what we're looking at, the work that we do in my lab is largely looking at neural control of human movement. And so we're interested in descending commands coming down from the brain, ultimately how we can incorporate those signals into how we control movement peripherally. And so ultimately we know when we're actually looking at movement control that we also have all of this sensory information returning back up to the brain. And so the big issue and why it fits into this realm here is that when we take people outside of Earth's gravitational field, ultimately the sensory input that we're receiving largely changes. So the loads on the muscles and ultimately all of the vestibular information that we're receiving due to the low gravity environment. And so as a result of being in a low gravity environment for extended periods of time, individuals returning from space often have gait and balance deficits. And so our interest here is trying to understand why that is, what the mechanisms are, and ways to overcome that. And so the methods that we use are a number that we can use to try to understand brain activity. Because we want to use low-cost portable devices that may even be used in real-world conditions like in space or on other celestial bodies, we can use electroencephalography, which is going to use very small sensors, lightweight, portable, little electrodes, capturing electrical brain activity, and it collects information at the same time scale as electromuscle activity or electromyography. During our assessments, we're often looking at collecting biomechanics or human movement measures, in this case, inertial measurement units, which is giving the body accelerations and rotations. Now, the EEG gives us all of these squiggly lines. This is electrical activity from the brain. It's on a very small microvolt level scale. What we can do with it is convert that to the frequency domain, look at the amplitude of the signal or the amount of signal across different frequencies, so the rate at which the brain waves are oscillating, slow up to fast. And by tracking changes in spectral power, we can understand cognitive processes that are going on and neural control processes, in addition to sensory processing up at the level of the cortex. So typically reduce, in this case, alpha power in the 8 to 13 hertz range, or beta power 13 to 30 hertz range, typically are going to decrease with more sensory processing or movement. Now, electromuscle activity, a little bit more straightforward in terms of collecting the signal and interpreting, still going to be electrical signals, but at the millivolt range typically. And the relationship usually is greater tension on the muscle activity in the muscle is going to lead to more of this noisy spiking activity. So our goal was to understand how is brain and muscle activity going to change in low gravity environments and when we perturb people standing in low gravity environments. Now, how do we work with low gravity environments here on Earth? Obviously, we have gravity acting relatively constantly throughout locations on the Earth. We can't remove the force due to gravity. What we can do is apply unloading forces through a number of different mechanisms, including upward forces through mechanical means or positive pressure, or we can place people in underwater environments, which was the topic of this study here. So we took individuals and had them stand on this treadmill, lowered them into the water, and collected electrical brain and muscle activity in a number of different conditions. So our first condition was having people standing quietly on land. Next, we lowered the individuals up to their chest level and then to their waist level. Ultimately, the lower the individuals go in the water, the greater the body weight unloading, simulating low gravity. We also introduced external fluid forces, in this case, to the front of the individuals from jets in this underwater environment to basically make the people off balance when they're standing underwater. Now, just to introduce some of the results, I won't get into a ton of detail, just to introduce the things that we took away from this study. We looked at electrical muscle activity in the lateral gastrocnemius here, medial gastrocnemius, and the soleus muscle, peeking out here. Each of the conditions here on the y-axis, we're looking at change relative to the standing condition. So 0 is no change, greater activity is positive, lesser activity is negative. And each of these conditions now correspond to the images I just showed, standing at chest level, waist level, and then standing underwater at waist level with either low or high external fluid forces. The thing to notice here first, the positive signs are going to indicate where we're seeing changes relative to the standing condition. The asterisks are going to be differences between conditions. But the major takeaway here is that the plantar flexors and things that are surrounding the ankle joint are going to be experiencing less electromuscular activity due to unloading. So predictable response there, what we would anticipate seeing. when we move up the body to the rectus femoris, vastus lateralis, and biceps femoris, and now spanning the hip and knee joints, rectus femoris, vastus lateralis, and biceps femoris, we don't see as many changes due to unloading or due to body weight support, but we do see once we start to apply our external perturbations, meaning the asterisks, relative to just body weight support, we're now seeing that the activity in these muscles is increasing. So again, predictable in the sense, we know we unload people, lesser muscle activity, we perturb people, greater muscle activity, and we see this also in the tibialis anterior. Now, excitingly, in the brain activity, what we see is when we actually take our electrical brain activity and isolate electrocortical sources, model them as dipoles, we can see where the activity is arising from. And we ended up with 3 cortical clusters from our participants: left prefrontal cortex, is a higher level of cognition, understanding where we are in the world, motor planning in the premotor cortex, left parietal cortex, identifying where we are in space relative to our environment. And what do we end up seeing? Again, we're going to look at spectral power on the y-axis, frequency on the y-axis. And so from each of these brain areas, what we're showing in each of these given frequency bands, theta, alpha, beta, and gamma. Ultimately, from each of the brain activities, the black bars are indicating where there's statistical differences between the conditions. The major thing we see is that there's significantly lower power, spectral power, when we're standing underwater with large external fluid forces, so placing people off balance. The other thing we notice is that the gray line is standing on land, and we actually see a spectral power increase in alpha band here compared to standing on land when we're unloading people alone. So just having people stand up to their waist or up to their chest underwater. So what does this mean? When we're seeing an increase in spectral power, we're basically identifying that we have lesser cortical involvement while maintaining balance in our simulated low gravity environment. So as we lose some of that sensory feedback, the cortex is less involved. And when we start to apply external balance perturbations, we see large decreases in alpha and beta band spectral power, and we see increases in theta, meaning we're processing more sensory information, we're having to more actively control our balance. So to get ahead of some of the questions that might come up, why are we doing this? If we can understand the mechanism for reduced cortical involvement to potentially losses due to sensory deprivation, ideally we can apply some perturbations to maintain regular brain processing. And the next step past this, already going on, is we're doing locomotion studies. So in similar conditions where people are walking underwater. From there, what is the potential application? Individuals with locomotor deficits, things like spinal cord injury, are often using assistive devices that are going to incorporate body weight support. So we're also doing overground testing and looking at applying body weight support in different ways. And so these studies are ongoing, followed up, but they will be soon published and related to the topics that are presented here today. So just quickly, I want to thank my amazing doctoral student, Sangmi Song, and all of our undergrad research assistants that assist Song in the data collection. Thank you very much.
Thank you so much, Professor Nowin. That was a lovely presentation. Now we are going to go to the very next speaker. Just please keep track of your time, because otherwise I have to unmute myself and tell you that the time is running out. And so guest speaker is Dr. Chu. Eunice, please.
Hi, okay. I'm going to share my screen. Okay, so hi everyone, I'm Eunice, and I'm going to talk about this paper by called Uniscope by me and Professor Kevin Xia. So in recency, as mentioned by other speakers, there are more space exploration projects in recent years because the cost of spaceflight has lowered by 10 times than it was a decade ago. So the space tourism is made more promising in the near future. However, many researchers have shown that microgravity has influential to human physiology, inducing anemic condition, and also make the red blood cells speculated, deteriorating the cardiovascular, neuroocular, and also skeletal muscular systems, and also altering the stem cells potency. So I think it is worth investigating the changes of cells under microgravity. But given like the limited resources to spaceflight, there are multiple ground-based systems for simulating microgravity. However, the ones for cell biology research are mostly very bulky, large scale, and provide no continuous morphological monitoring. So for that, some system incorporates the microscope, but then they lack reconfigurability due to the use of existing developed microscopes. Another motivation is that most of such systems are accessible only in countries with space exploration projects. So Uniscope, the thing that we developed in this paper, is a microscope incorporated microgravity simulating system, which can fill this gap. And Uniscope has 4 major features. First, it is compact with a smaller dimension, lightweight, and also easy to fabricate. Second, it incorporates an optical microscope for continuous imaging and morphological monitoring. It is important because microgravity can induce cell morphological changes that indicate health issues in astronauts under prolonged weightlessness. And third, we adopted an open source 3D printed modular microscope development platform UC2, so the microscope is reconfigurable for different imaging modalities. And the fourth major feature is that Uniscope is ground-based, so it can be used in places with less resources for spaceflight. So let me ask you guys a question. Does anyone here has a 3D printer at home? If you do, you can also make this system. Okay, let me show you. So Uniscope consists of a clinostat box, housing and fixing the microscope inside with a servo motor for clinostat rotation. And here comes the fun part. I used 2 open source systems for making the microscope, the UC2 microscope 2 box and also Raspberry Pi with a high quality camera for image taking. The UC2 adopts modular 3D printed cubes with size 5 cm to house the optical components inside. And then this base plate is to for secure the box for easier alignment. And some modifications have been made such that the system is more secure. And this whole system is designed using Fusion 360 and 3D printing. So all of them are easily accessible and purchasable. To verify its imaging qualities, we took images of various biological samples. They include grape skin, human red blood cell, and lung cancer. And to improve the image contrast, we adopt oblique illumination by adopting like a mask after the light source. And consequently, the details of an unstained specimen could be revealed in a pseudo 3D manner like this. Besides, the system successfully captured the disintegration of lung cancer cell membrane under full illumination, showing the capabilities for morphological monitoring. And then 2D clinostat was adopted as it is simpler and cost-effective in the performance in simulating microgravity. And using a rotational speed of 35 and 90 RPM, we can see that the value can reach up to 10 to negative 2 or 10 to the negative 3 in the order, respectively. And the G-force value along the X and Z axes oscillate between negative 1G and 1G, while that along the Y-axis is generally stable with minimal fluctuations. So this shows its promising potential to simulate microgravity. Our project is still ongoing, so let me briefly share our recent development. In the second phase, we modified the clinostat to RPM, that is random positioning machine, and developed a miniaturized UC2 compatible incubator named Amelia using microfluidics and lab-on-a-chip technology. And it successfully achieved a 24-hour of incubation of this human lung cancer cells under the rotation. And we're excited and believe that this system is useful for space health research in the future. And then last, I would like to thank IEEE for this opportunity and Dr. Bonato and Dr. Ila for this opportunity, and also Kevin for supervising this project. And I hope you guys love it, and you can test it if you have chance, and feel free to contact me for more discussion. Thank you.
Thank you, Eunice. I love to see young professionals so passionate about space. So thank you so much for sharing your work. And now it's time for Professor Ishikita Please, Professor Ishikita on the stage.
Good afternoon, everyone. Can you see my desktop now?
Yes.
Right. Okay. I'm Dr. Naoyuki Ishikita from Niigata National Hospital. Thank you for inviting me to the IEEE webinar. I'm so delighted to introduce my research. I work at Niigata, Japan, and have developed numerous medical instruments. Our mission is popularize simple, low-cost medical devices and ideas among doctors and patients. In space, one crucial principle to remember is that complexity kills, simplicity saves astronauts' lives. For example, anesthesia is essential for future space missions, but conventional anesthesia equipment is too large and challenging to operate and maintain in space. So I invented a 3D printable anesthesia system called BioJet. The key component, an artificial respirator, was successfully created in space in 2017. This technology now enables the production of artificial respirators anywhere with a 3D printer and an internet connection, no matter how far from now. It has undergone successful testing in zero gravity conditions twice and has received high praise from NASA astronauts. So today, I'd like to discuss airway clearance in space. Currently, the standard method involves blindly inserting a suction catheter connected to the suction tube into the trachea, which can be painful and lead to serious complications. To address these issues, we've invented a minimally invasive sputum aspiration technique called vacuuming connection device called the sputum-vacuumer. Sputum aspiration involves removing air from the lungs with the suction pressure, allowing the extraction of the sputum and the foreign bodies to the upper airways. Additionally, the device is so compact that it can be held between the fingers, that size, and it can be created in just 20 minutes using a 3D printer. The vacuuming process is involving the following steps. The step 1, chest auscultation, listening to lung sounds to identify atelectasis, sputum, and foreign bodies. Step 2, pressurized ventilation, applying 40 centimeters of H2O pressure for 3 seconds to expand the lung and improve oxygenation. Step 3, vacuuming, applying minus 60 kilopascals of pressure for 3 seconds after expelling air from the lungs to move sputum and foreign bodies from the lungs to the upper airways. Step 4, cleaning the airway using a suction catheter. Until symptoms improve, just repeating pressurized ventilation and auscultation, okay? Now, let me show you how vacuuming is used in the clinical settings. This video is being published with permission from the individual. Vacuuming offers several advantages. 1, just minimize the risk of airway damage by eliminating blind insertions. 2, it provides comparable effectiveness with simpler and lower cost procedures. This patient and the nurses appreciate that vacuuming is a painless aspiration technique, and the procedure time is shorter. This approach enables not only healthcare professionals like me, but also caregivers such as family members involved in home care to perform sputum aspiration without extensive training. By reducing dependence on expensive equipment, we can significantly improve patient care. In conclusion, we are seeking local and global business or research partners and collaboration opportunities. Please feel free to contact me so you can take a screenshot. Thank you for your attention.
Thank you so much, Professor Ishikita. That is so wonderful. I remind you that we are going to have one more speaker, and then we have open discussion. So you are free to write your own question in the chat, and the speakers have contact details in their on their publication. So just keep reading the special issue. Now it's time of Kimia. Please, on the floor.
I'm sorry, I had a hard time unmuting myself. I hope everyone have a great day today or a night. And thank you so much for IEEE for inviting us, as well as wonderful speakers. I was gonna applaud everybody's work, and if they don't mind, I will refer back to them, as my passion in life is actually process of designing and innovative biomedical hardware, especially using in a space and back on Earth. I do have a team of folks that I've worked with. I'm very lucky to learn from many of them, from a chief engineer of human research program to folks that are scientists and engineers and faculties and universities. Without further ado, I'm going to jump into this slide. Some of you guys might have seen this. This is my graphic representation of my abstract, as well as the work that we're doing. When we are talking about on Earth design, we are thinking about in-Earth uses and how the hospitals or how the configuration of the healthcare is. As Dr. Nowin actually mentioned, when we leave Earth, we will have some different health applications and intended use, and that is actually impacts the process of designing the hardware and how we build different equipment. As Dr. Ishikita mentioned, the size of those systems is very important. However, at Earth, when we are designing for biomedical application, we're thinking about the standardization across countries, from PDMA from Japan to CE marks in Europe to FDA on United States. Across the board, we have developed these standards and the quality control definitions to help to keep the healthcare standard and have some understanding of what are the needs and the risk associated with developing hardware across nations. Some of them is the healthcare quality may change, but some of these standards actually carries over in many, many countries. As we translate these devices from the hospitals to the ISS or spacecraft or the mission, depend on the mission, duration, the size of the vehicle that we have, and the capabilities that we have, the size of the equipment, the robustness, the quality, the use of it get changed. Also, the intended use in the space is a little bit different. As you think about it, in our population of patients, we usually look at a certain disease or certain folks that have been unfortunately compromised due to a disease. And when we are talking about the astronaut, they might be actually very healthy folks that have a degradation that may not even be at the stage of disease, but we want to understand how does that work as well. So the level of the diagnostic gets a little bit different in this case. Having a physician there help us to diagnose better, but in order for the physician to have that diagnostic, we need to have the reliable systems and hardware to be able to address their questions and be able to send back imagery on Earth, or have somebody be able to get those information from the vehicle and be able to communicate in a very cohesive manner to the power to be, or the person that needs to make the decisions. Now, when we are talking about bringing back that technology back to the Earth, there are certain technologies that actually developed for space that can improve healthcare on Earth, as well as healthcare across space exploration. Our goal in this paper was to bring awareness to all fields, being bioengineers, medicine, nurses, as well as the engineers that are building medical hardware for space application, and spacecraft engineers, as well as other folks that are making regulations, a little bit of understanding of how the systems is working and currently, and as we go towards the commercialization and having it risk-taking factors are different, and that in that setting, how does that this information should be translated, and how does this information should be maybe fundamentally a start of a best practices guideline for developing medical hardware and healthcare hardware, treatment, diagnostic, and even preventative systems for space. So as I mentioned, there are control processings that's out there like FDA waterfall or V diagrams for aerospace engineers very closely, but there are minute differences that makes a different approaches and different communication between the system. For example, the way the validations and verifications happens in medical devices in the beginning and the communication that goes between them is very different than when the customer verifications happens in the space industry. And those differences brings challenges when you have a brand new exploratory medical hardware development versus you already have existing commercially available hardware that you are trying to modify for a space. In addition, when you're talking about the brand new exploratory medical device, you have a user need that you're translating to requirements versus when you are trying to go from 2D space in industry and flying your hardware, you need to understand what are those requirements are and be able to meet those. And as the environments are different, the testing requirements are different as well. Well, we understand this very well. We have been doing this flights for many years. We have kept our astronauts alive, as folks mentioned, but keeping them alive is not the only thing we want to do. We want to make sure they're healthy and happy, and we bring whatever that we learn back to Earth. Currently on ISS, there are several medical diagnostic systems and also treatment devices. One example is ultrasound. You can learn about the case study that I mentioned in that paper with my colleagues and changes that has been done in that ultrasound in that paper as well. But one of the things that came out of this ultrasound development in early 2000, I want to say, time frame that they were looking at developing the ultrasound was how do you downlink, how do you communicate, and how do you actually do a telemedicine. And that was actually, with the help of GE, translated back to Earth. And now GE has that capability back to folks in the hospitals and patients in the house to be able to work with telecommunication. The other aspect is when you have a novice person using the technology such as imaging that is very complex, you need to have the keys to communications to be able to make it simple. So as you see on the left side, there is a color coding map for our crew members to be able to use that and talk to sonographer on Earth to be able to do imagings, and many others. So by the time that this hardware was ready to be flown, is no longer is the device that was bought off the shelf. There has been so many changes happen to it. So the safety of the hardware is not only on the shoulder of the engineers and the if you want to say the agency that is flying this and doctors, is actually across the board, is multiple different disciplines that is actually put hands on this to make sure that we provide the best healthcare we can, and then translate those information back on Earth so that people on Earth can use the health application as well. So I hope the people that are reading this paper have to see the tip of the icebergs and appreciate the complexity that goes into this, and also the hope that we can, by commercialization, open this innovative area so that people can actually do more work and bring and increase the healthcare standards, both for space folks and on Earth folks. And I had a huge thanks for many, many groups that helped me be able to put this paper together and learn about all of those guidelines and build the hardware as well. And again, this is not a perspective of NASA, this is just my perspective. So thank you so much.
Thank you so much, Kimia, and thank you so much to all the speakers. That was great. And now we try to summarize what we have seen so far. And so Dr. Leine introduced us the needs for having more autonomy in terms of medical care in the future. Professor Nowin guided us in understanding the importance of using even underwater environment or swimming pool as analog for reducing the gravitational pull. Eunice, or Dr. Chu, she presents the wonderful device for increasing the use of, for facilitating studying astrobiology in any sort of, at the lower cost, I would say. Professor Ishikita presents us a wonderful device there is now use in Japan that could be used potentially also in space. And Kimia presents us a wonderful work about the importance of translating and understanding why certain device can be used in space and why some other device cannot be used in space. And so it is time now for having a little bit of discussion with our speakers. And so you're free to ask as many questions as you would like to. And we're trying to build a little bit on and to understand the needs of. So you see now that there is a lot of layers in innovation in healthcare and space and how the two closely relates. And I would like to kick off with a question that was in the chat before. That was related about nutrition. So nutrition absolutely impacts the way in which, countermeasures are also designed. And I wonder, and I have a question for Dr. Leine. What do you think about nutrition, how that relates to your work? Do you guys consider nutrition when you're planning countermeasure, you're planning future mission? Is that really important for a biomedical engineer or biotechnologist that is working in the field of space?
Yeah, that's the short answer. That is, yeah, to all of it. We consider it. It's important. Think about what was going on. The example I gave as a kind of a short one of scurvy. This was an unknown disease at the time in the 1700s, and people would send ships over, and it was basically you 50-50 shot of whether you returned, probably less. But through the innovations of researchers and some enterprising ship captains, they actually did experiments with growing food on board their ships and feeding it to the sailors, and discovered that the ships that did that versus the ships that didn't would have better outcomes. So in nutrition is critical. You can't do anything unless you have the building blocks to build your own body. So yeah, it's considered. There's a whole division of it at NASA, actually.
Yeah, that's true. Absolutely, that's true. It's considered a countermeasure. And when you read about countermeasure, that all the speakers can tell you more in their own respective fields, but it's one of the most important part. You can think about, for example, the physical activities without proper nutrition in space, and when the astronauts go back for rehabilitation as well. And I have a question now for Eunice and Professor Ishikita. Both of you have worked on 3D printing devices and trying to provide innovation in that. And I wonder, do you think really 3D printing can innovate also the field of space? Can it really, do you think it's really feasible? How far do you see that is going to happen, and how far that would be relevant for you and for your space agency, for example?
From my knowledge, sorry.
Yeah.
Yeah, you go first. You can go first. Yeah, you go first.
You first, please.
Oh,
please.
okay. Okay, thank you. So from my knowledge, I know that actually 3D printing has been used for space exploration projects, especially bioprinting. But then, yeah, so actually they have already tested bioprinting in space. So I think why not hardware, right? So for our project, 3D printing can print parts, and then we can use modular system to make them together to function, and then to use in space or on ground, and to simulate the space environment. So not only putting them all in space, because it's very, like scarce resource, and it's like you need many human power and also energy to go up to space. So for us, we think that actually we can do it on ground first, and then to do the validation at the same time on space. So 3D printing is a very good technology for us to do it on ground and also in space. So what about Professor Ishikita? Yeah, thank you.
Yeah, thank you. The 3D printing technology is really, really useful for the space missions. And I only use the material with the ABS plastic because the NASA only bring the ABS plastic in space. So I concentrate on use the ABS plastic, then made the ventilator and anesthesia attachment, and already tested on the zero gravity situation, and it worked. So it can be useful for the space mission and also the isolated island or emergency situation on the Earth. So this is great technology.
This is wonderful. And so I know now that I can use 3D printing for come up with any sort of device. And if I'm going to have it, I would like to send it to space. And so if I were, for example, a company and I have a device, can I just like call NASA or ESA or any other space agency and tell them, hey guys, just fly my own device because I just want to work in space. Does it work in that way, Kimia?
Currently, no. Unfortunately, that's an unfortunate answer. I wish the space was unlimited and we could have done that, but everybody and flown their hardware and they would see it. There's currently for agencies, there is a selection process that going in. However, as the space expanding and there's a SpaceX out there, there's other commercializations out there, there's Blue Origins out there, there's national labs is out there, that they are actually expanding on doing technology demos. They are capable of doing that. If you want to test your hardware on a crew member and get a result on that, that's also a different procedures. You mentioned about 3D printing in space. I just want to add 2 components to that. Depends on what kind of a material you're using in the space. And we have a wonderful suite of the 3D printers on Earth that we can do anything we want with it. But when you're talking about in space and you're talking about in the environment of a metal box and a lots of chance of combustion, any material that is melting and has a different types of melting point may have a different interest for being certified for space use. ABS, although that exists as a 3D printer on orbit, it's not very recommended for flying for space at current moment. It's great that we have ABS 3D printers on orbit. It's great that we have a tissue engineering. We have demonstrated tissue engineering on orbit, but that's the case. And as far as the nutrition and pharma goes and all the impacts that may happen, there exist standards out there. Unfortunately, I did not have enough time or bandwidth to cover it in my paper. I hope people do look at those things as well.
Thank you, Kima. Dr. Leine, please.
Another thing that's not often considered is the effect that the actual device or compound or whatever you're using would have on the closed environment of the capsule. So currently, when you have there has to go through a pretty extensive clearance. Think about the new car smell you have, which is all the plastic stuff that's being wafted off of the materials that were made in the car and into the cabin of the car. When for a small amount of time, that's probably okay to tolerate. That's an open question of research, by the way, but it probably is fine. In a space capsule, you don't have the ability to open the window and air out the cabin, though. So that stuff just builds up, and that can have some pretty significant effects, even if it's just mild headaches. A mild headache on an orbital mission under high stress conditions can be a real problem. So those kinds of things have to be managed, and the thing has to be able to clear vibrations and exposure to radiation, all kinds of stuff like that also.
Thank you so much. So now I know that I need a space nerd for creating a medical device. Now, I would like to close the discussion now, asking you one very last questions. Kimia, come on. Do you want to say something?
Yeah, just go back to Leine. Sorry. It's a very good point that you make, but what we have forgot that we actually did those things for Earth medical devices and medical use as well. We had actually built fundamental standards from being ESDM standards to ISO standards or anything else. And that's what I was pushing back on, saying, what is the best practices and guidelines that we will have in the future? And depend on the vehicle, that may change, depend on destination, that may change. And these are the things that, as not only engineers that we build the hardware, but also the physicians that we are communicating, we should be able to come together as a community and everybody else. I'm not just saying the physicians and engineers are the people that should be thinking about this. I think the political officers and everyone else as well should be thinking about this. We should think about what is the best practices that we might want to be thinking about.
I think it's wonderful, and it's a good point that you are making, Kimia, that it's a multidisciplinary efforts, either from the scientific team that is working hands-on the device and from the society. I do have a question for Professor Nowin, and this is a question that any one of you is welcome to answer. Now we see that a lot of people are going to space, like you actually don't need to be a former astronaut, professional trainee astronaut. And I wonder, what is the impact on having space tourism in your respective field? Professor Nowin shared the importance of using underwater swimming pool and unloading people from gravity force for understanding balance. And I wonder, how do you see, Professor, that apply to space tourists?
Sure. I mean, obviously, astronauts who go into space have to go through a rigorous training process. And so if you're sort of not having to go through that, then certainly you may not be as well prepared. But we do have some of those abilities to train people on Earth, maybe using some of the methods showed here today. Hopefully also, some of the metrics that we have could also be used as sort of biomarkers to know if someone may be more susceptible to, deleterious effects of being in a low gravity environment. And hopefully over time, we also have mitigation efforts that can be taken up into orbit as well.
Oh, that's wonderful. And so you see that there is a close connection with the expansion of the commercial space sector and with possible application even for space tourists. And I wonder how do you see, like, is it hard for you for your work that you show in the presentation that it can be also relevant for people on the ground that have specific medical condition or are undergoing rehabilitation, for what I understood. And I wonder, is it really directly applicable to this type of population, or does it need translation for being used for supporting research in specific fields?
Right. So I think, as I showed towards the end, obviously bodyweight support is used in a number of different areas. Microgravity is a unique one. But certainly using some of the methods, that I showed briefly today, at least, unloading through various mechanisms is very common in rehabilitation, but being able to actually track what are the neural adaptations during the rehab process. Are we restoring people to baseline, and really, coming from the neuroscience perspective of really understanding how sensory information is being processed, and trying to restore all of that in addition to just the physical rehabilitation, the sensory rehabilitation too.
Thank you so much, Professor Nowin. And I wonder if any of our panelists would like to share a little bit of insights about their own perspective on the on having so many space tourism in space flight. What are the implications? How do you see that impacting in your research field?
Well, here, I'll jump in for a second. Quick answer to that is I think it's awesome. I think space for everybody is a real valuable prospect. And right now we have about roughly 700 people that have ever been to orbit, most of them, or into space, and most of them are very short duration, either suborbital or a couple of days. We need more research. We need more data, and putting more people into space from a medical perspective is going to give us that data. Also, more people should go to space. We have, there's brilliant people, capable people all over. So I think finding ways to increase access to it and learning more from that is a huge boon.
Thank you so much, Dr. Leine. And meanwhile, I would like to introduce you to a very special guest speaker, because we had to, keep up with the program. Otherwise, we will start chatting and chatting and chatting. So the two guest speakers that we have today are Professor Russomanno and Professor Berengueres. And I invite you to unmute yourself and to have an open discussion with us. Please feel free to write any question that you want me to ask the speaker in the chat. And I invite the speaker as well to answer directly the question and to engage with participants. Most of them are very specific, like, like the use of surgery in space and other details, or there is a question even for Kimia here. You might want just to reply directly in the chat so that, we can support participants. So Professor Berengueres and Professor Russomanno, thank you so much for joining us. The two have written very specific and forward-thinking papers still in the special issue. And I would love to talk to you about something very futuristic, because as far as I know, we are going back to the moon, like Europeans say, but actually Europe never went on the moon, like the United States went on the moon. we are just claiming benefit. And right now we are, but also, I'm just kidding, but seriously, the European Space Agency is also active in the future mission to the moon, together with other emerging space agency and formal space agency. And I wonder, what do you see are the greatest innovation in space healthcare when you think about the future? So let's forget for the moment about the International Space Station and let's focus on the moon, please.
Well, thank you, Ilaria. This has been so enlightening and interesting and exciting conversation. So I want to go back to what Dan Levine said about that we are in this scurvy moment, right? When we send people to space, they come back with muscle atrophy, but we don't understand very well why. We now know that the microgravity disrupts the cell pathways and how T cells work and so many other things that it's like counterintuitive, but why, right? And so we're in this scurvy moment, and how we're gonna get out of it. And I was thinking, wow, we might need help of AI and things like AlphaFold, but for microgravity, right? Because it's all about the proteins, and then identify which proteins don't work in microgravity as they work on Earth, and so on. And I'm thinking probably all this can be solved with a small pill. So I'm thinking when we go to Mars, the astronauts will have to kind of get their daily dose of vitamin C, but this thing that lets them arrive safely. And I think, remember when NASA went to the moon, we developed so many things like aluminum foil and things that we are using now, like digital twins as well, right? Developed by NASA there. And I think this is such an opportunity to push science and medicine forward. So yeah, that's my 5 cents. And this is a very, very exciting moment.
Thank you so much, Professor Berengueres. I wonder, Professor Rusumano, you have been teaching space physiology and space medicine since forever, and you're also a flight surgeon. And I wonder, from your perspective, from your point of view, what can be the greatest innovation fields for working and contributing to sending humans on the moon?
Well, I think that we are in a very exciting moment in terms of space science, especially in the area of human space exploration, because you are facing 2 different challenges at the same time, which is to send tourists into space, people that are not as fit as astronauts, not as selected and trained as astronauts, and then you are going to have huge medical issues that might happen to them, because they will be less fit with chronic diseases and medication and so on. We know very little about pharmacy in space, how to prescribe drugs in space. We basically export what we know, what we have here on Earth for astronauts to use. And we are also changing the profile of our exploration in terms of led more by space agents, which is to return to the moon and one day go to Mars. So it is really a huge challenge, because as a doctor, a medical doctor by training, and I later on a space doctor, I can tell you that we don't know enough. So when you talk about innovation for healthcare, for space, and innovation in these areas, I think that I agree with Levine, we need much more research. I think that we need to concentrate on research in space more than analogs here on Earth. I've been working with analogs for decades, and not just the clinostats that was discussed here, but head-down tilt, body suspension device, Alter-G, treadmills, and so on. But we know that it is whatever we get from this equipment, from this type of protocols, they can contribute with the knowledge, of course. We are always getting some kind of good results out of our research, but it is in terms of extrapolating the results to space, to try to better understand how the human body works in space, I think that it is still very limited. So when you talk about innovation in space, I think that we concentrate a lot in technology. And I think that we need to really create the knowledge first. That's one point. The second point that I believe that we need to be more interdisciplinary in every single aspect of research or activities, projects in human space exploration. I'm very happy to be here, seeing all these projects being presented. Congratulations to everybody that presented today. It was completely by chance in my life that when I started a long time ago, as Ilaria said, forever, is telling my age, that nobody wanted me in the School of Medicine, because they couldn't understand our space physiology, medicine, what is this young lady wants to do. At that time, I was very young. And then they put me in an institute where it was basically run by engineers. And it was the best thing that happened to me, because we started building things, we start interacting, students, professors, researchers from the technical areas with the health areas, not just medicine, pharmacy, psychology, nutrition, physiology, and let's say the engineerings, as I used to call, biomedical engineering, electrical engineering, and so on, plus computer science and so on and so forth. So this is something that I feel that it is lacking sometimes. We are still in different, let's say, boxes, and we need to come together, because the huge innovation will come by building up knowledge, and we do not have this knowledge. Very unfortunately, 60 years plus after Gagarin the first flight, human flight to Gagarin, 1961, we still lack lots of knowledge in relation to how the body works in an extraterrestrial environment, body and mind. So I think that's, and I feel very happy to be here. I congratulate the initiative of creating this issue, the special issue relating healthcare, space, and technology, bringing different areas, and we need much more issues like that and discussions like that.
Thank you so much, Professor Somano. So it is really important building knowledge and work in a multidisciplinary team. Unfortunately, from my own experience, it happened that the space sector is so challenging, but it is fantastic, because you can't win alone. The team is really important, and to build knowledge. And so regarding to knowledge, I have a question for Professor Berengueritz. I've read on your paper that you guys are working on a very specific topic. And the reason for which I'm trying to bring it up, because the senses, human senses in space, are kind of overlooked in the past as far as concerned my knowledge. And I wonder, how do you approach that type of topic? If you can briefly cover some details about your ongoing work, please.
Right, yeah, I'm sharing my screen. Can you see it?
Yes, we can.
Yes, excellent. So very briefly, the project we're doing here in United Arab Emirates is just improve the spacesuit, and we're just reading some reports from the Apollo program that astronauts fell a lot, and why is that? So we decided to kind of let the astronauts feel what they're doing with their hands a bit better, and the results we got are quite things. So there's this effect called the sensory deprivation, that is that when humans cannot feel the normal environment, sounds, tactile things, the cognitive load increases a lot, and then they become less smart, which is something we want to avoid completely, right? So this is the research we're going here, and the results are pretty shocking, like the effects of making a spacesuit, for example, sound transparent, so the astronauts can hear the simple sounds they do when they order a puzzle, completely changes how fast they can solve a puzzle, which is kind of puzzling. So that's what we're doing here. And sensory deprivation is just one little thing. And we have all the proteins, how they change and so on. So there's so much to learn here. And so, yeah, it's a very exciting. And I recommend all the attendees, if you're interdisciplinary, this journal is great because they're very friendly to interdisciplinary research.
Fantastic. Thank you so much. So in conclusion, I have a question for all of you, and I want an answer from all of you. So get ready. If someone wants to work with you or would like to start working in the field of space and healthcare, what are your recommendations? I remind you guys that you are an international panel speaker. So I would kindly ask you to mention your country, because I have been immigrant for 10 years in my life, and I know how different is the work environment between countries. And so I kindly ask you to mention the country where you work and to provide some insight or some information about how can people join, collaborate with you, or collaborate in the field of space healthcare in your own country, please.
Right, I'll go first. So we are in United Arab Emirates. Now there's a big push with grants for Mars exploration, for example, anything related to Mars, how to build a base, space suits, etc. So if you're into that, please contact me.
Professor Russolano.
Sorry, I was waiting for, I thought that the others would answer as well. So yeah, I think that it's, in my case specifically, I would like to better connect artificial intelligence and human space exploration, because I believe that, as it was discussed here many times, we need to have crew space travelers that are more autonomous in their decision, their the ability to perform a diagnosis and start a treatment, managing diseases and emergencies in space. So this area of connecting AI, computer science, and medicine and other areas related to healthcare in space, for me, it's a top area nowadays. As I don't believe that we will have time to build up the knowledge that I would like to have to send safely tourists into space and people living on the moon or Mars one day. And we need to protect ourselves now, protect these travelers somehow. And I think that the possibility of adding a very sophisticated AI system related to medical issues in space will be extremely important, and that's, in my opinion, now is the only way out.
Thank you, Professor Russolano. And now we go to Professor Ishikita.
Oh, no. I believe simplicity is the saves the astronauts. So please join my research. And telecommunication is all. I can communicate with the telecommunication, but please come to Japan and then drink together and talk more. Thank you.
I love it. Drink together and talk more. Fantastic. Thank you, Professor Ishikita. Eunice.
Hi guys, I'm in Toronto and I actually just graduated from my master's studies. So if you're seeking like collaborations or such, you can like contact me, because I'm also seeking opportunities for further studies in PhD or something like that. So yeah. See you guys.
Thank you, Eunice. Thank you so much.
Thank you.
Professor Nowin.
Hi, so I'm also a guest in the United States, but I'm at Texas A&M, so obviously I do human subject testing, sensor development. Happy to talk to anyone who's interested in those areas. I think the one elephant in the room is we're all a bunch of enthusiastic researchers, but getting money, finding money to do the research is obviously a very important thing. So having access to those funds is obviously one of the things that's going to continue to drive the research and innovation. So, perhaps we still have the traditional funding mechanisms like the national institutes and foundations, but maybe with, continued space exploration and the private sector in that space, perhaps there'll be other mechanisms moving forward as well.
Thank you so much. And now it's time to Dr. Leine.
This is a pretty hot issue right now in the US, so I'll be careful about my responses, but there's a lot of changing work happening in the space medicine education, or at least on the clinical side of things. If you're interested in research in that, there are plenty of opportunities for, as you said, you have to acquire funding, and one example of that would be Trish out of Baylor College of Medicine. They do a lot of funding and research in the clinical in the space medicine space. But if you're interested in training in healthcare, it's been limited to national programs. I'm actually presenting on this at a separate conference in Abu Dhabi next month to discuss about international possibilities. The short answer to it is it's growing. The field is changing dramatically, so stay tuned. It's going to happen. There are ways, but right now it is for the moment hard to predict what those ways are going to look like. So they'll be there.
Fantastic. Thank you so much, Dr. Leine. And Kimia, it's your time.
Oh my God. Okay, so first off, for those of you that hasn't figured out, but my ginormous accent, English is not my first language. I am Iranian American. I am an immigrant. As you mentioned, the countries will have conflicts, but that doesn't reflect on what you want to do and what your passion is in life. Don't take no for an answer. I did not take no for an answer. Dr. Leine can actually said that I don't take no for any answer. I will keep asking questions. I'm in this field because I was disappointed in bioengineering. I'm going to say it. I was a biomedical engineer, work in the field, and I wanted to see more innovation, different types of innovation. And oh boy, I saw different types of innovation, and I saw different passionate people doing different things. I think it's great that we are becoming multidisciplinary field. I think there is a place for everyone with a different view in this field. And I think as long as we are continuously communicating, there is opportunities that opens up in the ways that we never thought it would be even possible. Being a bioengineer in space application, yes, there's not much of a space regulations that you can go and open the book and learn about it. But there are many programs that now allows you to fly. You don't have to be an ISS to do a research on biological system. You can go on a satellite and still get your data on your cells, your animals, and learn about what you can do. And that can help our healthcare. Every single little thing that we can do about what we can learn on different environments, the different adaptation and the complexity, it helps our future. And whoever wants to know more about it, and if I ever can help, my emails is on my paper and I'll be happy to help.
Fantastic. So I thank you so much for all the speakers. I thank you really, the editor-in-chief Bonato and all the reviewers. The reviewers usually are not mentioned anywhere, but we use a lot of reviewers. So thank you so much. And, you know, this was an important special issue for me. That was my first special issue, and that was very close to one of my personal life mission, which is bringing more space in healthcare and vice versa. So I thank you so much for listening, and I'm wishing you a good evening and a good weekend. Goodbye.
Thank you all.
Thank you very much, everybody.